Would you ever have believed that the new space telescope would bring us so many groundbreaking discoveries? The James Webb Telescope has now even found an ancient structure that is home to a trio of quasars. Quasars are brightly shining phenomena inside galaxies and are among the most massive structures in the universe. James Webb is an extremely powerful telescope that can capture light levels so low that no other telescope before it has been able to pick them up. This means that we can now see further into the past than ever before. Since the summer of 2022, James Webb has been the world's leading space science observatory, and each new discovery is eagerly awaited. Now, the new sensation is imminent as James Webb will study some of the oldest quasars in the universe. Quasars are a type of active galactic nucleus surrounded by a disk of gas that orbits the black hole, emitting enormous amounts of radiation. Although quasars are among the brightest objects in the universe, they have been extremely difficult to spot. In fact, even the newest objects of study are so far away that Webb only receives very faint signals from them. It is thanks to Webb's excellent technology that these objects are now visible to us at all. Thanks to the unusual angular resolution, the telescope can reliably separate the light of the quasar from its host galaxy, providing us with details never seen before. Researchers will now use all the technical refinements on board the James Webb Space Telescope to study three of the most distant quasars. The James Webb Telescope has four main instruments that can collect and analyze light from distant stars, galaxies, or in this case, quasars. The near-infrared camera, NIRCam, can record images in the near-infrared range. This new imaging technique makes it possible to capture light that is far away. The near-infrared spectrograph, NIRSpec, is an instrument that breaks down the light of distant objects into its components to obtain information about their chemical composition and movement. The mid-infrared instrument, MIRI, records images in the mid-infrared range, allowing researchers to trace the formation of distant objects. The Fine Guidance Sensor / Near-Infrared Imager and Slitless Spectrograph, FGS/NIRIS, is used to determine the position and distance of distant objects in space. Using these technologies, scientists will obtain brand new measurements of quasars and the masses of their central supermassive black holes. They will know how many stars are contained in the galaxies and explore the composition of their host galaxies in detail. The quasar trio consists of J0313-1806, which already existed 670 million years after the Big Bang and whose black hole is 1.6 billion times more massive than our Sun, J1711 plus 2115, discovered around 700 million years after the Big Bang and is 1.5 billion times more massive than our Sun, and J1342 plus 0928, which existed 690 million years after the Big Bang and has a galactic center with 800 million times the mass of our Sun. These observations give scientists the opportunity to understand more about galaxy evolution and the formation of supermassive black holes in this early era of the universe. When James Webb looks deep into the universe, we are actually looking back in time. The light from these distant quasars began its journey when the universe was probably still very young and took billions of years to reach us. When we look at objects like the quasar trio, we see them as they were a long time ago and not as they are today. No one knows if these galaxies still exist today, and if they do, they have moved very far away from us. All three quasars existed when the universe was less than 800 million years old. In James Webb's images, the light from these very distant objects appears red due to an effect known as redshift. The further the light has to travel, the more it is shifted towards the red light spectrum. The visible light emitted by the early universe is so extremely stretched that it is shifted into the infrared range. James Webb was specifically designed to collect light in the infrared range, making it possible to study these ancient and distant quasars. The quasars that scientists will soon be studying in detail are not only among the most distant in the universe but also among the brightest. Not only do these quasars form around black holes with the highest known masses, but they also have remarkably high accretion rates, meaning that a lot of material falls into the black holes. The enormous amounts of matter sucked in by these black giants continue to power the quasars and their jets. Compared to the turnover of these black holes, the black hole at the center of our own galaxy is relatively harmless, as it hardly has any matter being sucked in. In the 3 galaxies that Webb will study, the amounts of energy released are enormous. The streams of energy spread out in huge waves in the host galaxies, driving massive star-forming regions. These outflows of energy are thought to play an important role in galaxy evolution throughout the universe. In some cases, the outflows of gas, dust, and energy are so powerful that they throttle or stop star formation within the host galaxy completely. Scientists suspect that these outflows could even affect regions far beyond their own galaxies. Quasars are bizarre objects that feed on infalling matter, creating fantastic streams of radiation. The light from a quasar at the center of a galaxy can shine brighter than all the stars in its host galaxy combined. Some quasars emit jets and winds that reach far beyond their galaxies. Researchers now want to understand what role this galaxy activity played during the era of reionization, when the hazy universe slowly became clear more than 13 billion years ago. During this era, the universe was probably still very young and not as clear as it is today. The era of reionization is considered one of the most important frontiers in astrophysics. Research teams hope to use quasars as background light sources to study the gas between us and the quasar. The gas observed in this way absorbs the light of the quasar at certain wavelengths, and imaging spectroscopy can visualize absorption lines in the intervening gas. The brighter the quasar, the stronger these absorption line functions are, which should help scientists determine the neutral or ionized state of the gas and understand the reionization process. James Webb's mission also includes the thorough investigation of hundreds of exoplanets. For the first time, it will be possible to examine the light waves around distant planets in great detail to determine which of the planets with the highest Earth similarity index really resemble our home and are possibly inhabited. James Webb has already demonstrated its excellent capabilities with an analysis of the exoplanet WASP-39b, revealing the molecular components of its atmosphere in great detail. WASP-39b showed similarities with Jupiter but is significantly hotter, with components such as carbon monoxide, sulfur dioxide, potassium, sodium, and water. Webb also examined some planets from the TRAPPIST-1 system, where several planets are considered Earth-like candidates. The 7th planet, TRAPPIST-1g, is most likely enveloped in a thick hydrogen-rich atmosphere and is classified as a heme world. These planets consist mainly of water or hydrogen but are not necessarily life-friendly. Thanks to Webb's analyses, TRAPPIST-1g turned out to be a hot soup of sulfurous oceans. This new data provides exciting insights into the early universe and the potential for discovering habitable worlds. As James Webb continues to make groundbreaking discoveries, scientists are particularly eager to explore the implications of its findings for our understanding of cosmic history. The detailed observations of these ancient quasars and their environments will not only illuminate the conditions of the early universe but also shed light on how the first galaxies and supermassive black holes evolved. This deep dive into the cosmos could potentially reveal new insights into the fundamental processes that shape the universe as we know it. Moreover, the ability to capture and analyze the faintest signals from the most distant objects underscores the incredible technological advancements achieved with the James Webb Telescope. By examining the chemical compositions and physical characteristics of these early quasars, researchers hope to gain a clearer picture of the conditions that led to the formation of galaxies and the role of quasars in cosmic evolution. Each new discovery made by Webb adds a crucial piece to the puzzle of our universe's origins. In addition to studying ancient quasars, James Webb's exploration of exoplanets is paving the way for future discoveries in the search for potentially habitable worlds. By analyzing the atmospheres of distant exoplanets with unprecedented detail, Webb provides valuable information that could one day help identify planets with conditions similar to Earth. This capability is essential for understanding the potential for life beyond our solar system and advancing the field of exoplanetary science. As Webb continues to unravel the mysteries of the universe, the scientific community remains enthusiastic about the future discoveries and revelations it will bring. The telescope's cutting-edge technology and its ability to peer back in time to the universe's infancy hold the promise of answering some of the most profound questions in astrophysics. The ongoing research and findings from James Webb will undoubtedly reshape our understanding of the cosmos and inspire further exploration of the universe's many wonders. The James Webb Telescope's discoveries have already begun to challenge and refine our current models of cosmic evolution. As researchers analyze the data from the quasar trio and other ancient objects, they may uncover new phenomena that could lead to revisions of existing theories about galaxy formation, black hole growth, and the role of quasars in the early universe. Each finding from Webb not only expands our knowledge but also prompts new questions, driving further research and exploration. The observations of quasars from such a distant past also provide crucial context for understanding the development of large-scale cosmic structures. By studying these ancient objects, scientists can better understand the interplay between black holes and their host galaxies, including how feedback mechanisms from quasars might influence star formation and galactic evolution. This research could reveal new aspects of how early galaxies matured and how their central black holes shaped their growth. In addition to its contributions to astrophysics, the James Webb Telescope's findings have significant implications for cosmology and the broader scientific community. The data collected from these ancient quasars and exoplanets will be instrumental in refining our models of the universe's history and the processes that govern its evolution. As Webb's observations continue to unfold, the telescope is likely to become a cornerstone of modern astronomy, influencing research across multiple disciplines. Looking ahead, the continued success of the James Webb Telescope will depend on the ongoing collaboration between scientists, engineers, and researchers worldwide. The telescope's ability to reveal the most distant and faint objects in the universe relies on the collective effort of the global scientific community. As we anticipate future discoveries, the excitement surrounding Webb's mission will undoubtedly drive further innovations and inspire new generations of astronomers and space enthusiasts. Thanks for joining us on this cosmic journey. Remember, the universe is vast and full of wonders, keep looking up. If you have a specific theme or focus for the video, I can tailor it even more.